So today we'll wrap up chapter 6. Oh, sorry, not 6. Chapter 3. Except for like one problem, should be able to cover everything else. So, all right. So I believe we stopped here after introducing capacitors, right? So let's look at a physical construction of a capacitor. So capacitors are two parallel plates separated by an insulating layer, right? The physical description of a capacitor is two parallel plates separated by an insulating layer. The equation that governs the capacitance is given by C equals epsilon A over D. Epsilon is the Greek letter epsilon, epsilon A over D, and it's used to note the permittivity of the material. So epsilon is further given by epsilon 0 times epsilon R. Epsilon 0 is the permittivity of vacuum. It's a constant, 8.85 into 10 raised to minus 12 farads per meter. Epsilon R is the relative permittivity of the material of the insulator, okay? Or the dielectric, if you will. Okay, so epsilon R is the relative permittivity of the dielectric material. Similarly to permeability, right? Mu was equal to mu 0 times mu R, which was for inductors. Here you have epsilon. Now, D is obviously easy to understand. It's the distance between the plates. Capacitance is inversely proportional. So the farther apart the two plates are, the lower the capacitance. The closer the two plates are, the higher the capacitance, right? How about A? A is basically the area of either plate in square meters, but it requires a little bit of explanation. This sentence would be true only if both plates were exactly the same size and they overlapped exactly the same place. Make sense? But if they were of equal size or unequal size and overlapped only at certain place, which A would you take? Just the overlap, exactly. So overlap, and again, by the basic definition of capacitance, it is two plates separated by an insulator. You don't have two plates where there is no overlap, right? And so the overlap is the area that you would take. Now, real life capacitors are not built like real life capacitors, of course, are made out of equal plates or equal size. And so that's not crucial. But again, the microchip example that I used in last class, where we have overlapping wires or conducting wires separated by an insulating material, that's a very real life scenario, right? So it's the overlap. And there you have it, A over D. Larger the surface area, the higher the capacitance. Yes. Yes, that's the, yeah. Yeah, thank you. I do this every quarter. I keep forgetting to change this. I need to change that slide. It's epsilon 0. Let's see, what was I saying? Oh yeah, so A over D makes sense, right? So that's the physical description of the capacitor. Again, simple equation, but I don't expect you to memorize it. I mean, if you remember it, that's great, but you can have it on your equation sheet. So if in the exam you have a problem, I mean, the problem statement asks you to solve for the capacitance, you look up the equation, but then you should understand A, D, and the epsilon, right? You should be able to like apply those principles and determine the capacitance. Okay. So what exactly happens when you connect a capacitor to a voltage source? Now, I assume from physics classes, everyone is familiar with the concept of electrons moving in a circuit or moving in a wire, hopefully. And You're familiar with the statement that current flows opposite of the flow of electrons. You hear of that, right? So now, semiconductor physics, or well, just physics in general, electrons have negative charge, right? You have a balanced charge. When an electron leaves, when it leaves its position, you have a net negative charge or -1 negative charge, right? So what is left behind? Left behind is a hole. It's an empty space. In electrical engineering, semiconductor physics, that the technical word for it is a hole, HOLE. I don't know if you all have you all learned that in physics, perhaps? No, a little bit. Okay, so absence of an electron is defined as a hole, HOLE, and a hole is said to have a positive charge. Again, absence of an electron, absence of a negative charge results in a positive charge. Anyways, the way it relates here is that the concept of electric current is that it always flows the opposite of electrons. That is not completely true because in electrical engineering, there are some analyses that require a hole flow. Okay. Electron flow current is basically the same direction as the electrons. Hole flow is basically what we use as the opposite of the flow of electrons. Okay. And so if you look at the circuit right here in A, you have a capacitor that is connected to Vs. The switch is not yet closed. The switch is open. Okay, the switch is open. And the capacitor is said to have 0 volts across it, meaning the initial state of the capacitor is fully discharged. Yeah, it's completely discharged, doesn't have any stored energy. Then at some point, the switch is closed. When the switch closes, what happens? We all know like charges repel and opposite charges attract. So voltage Vs is connected to the capacitor. The positive terminal of the voltage source will attract the electrons in the wire and the plate of the capacitor. Keep in mind that the capacitor is separated by an insulating material. So nothing can actually flow through the capacitor itself. But the electrons on the top plate are attracted by the positive terminal of Vs. When the electrons move away from the plate, they leave a positive charge behind. So there is a buildup of positive charges on the top plate. All with me so far? And then what happens at the other end? The exact opposite. You have the negative end of Vs connected to the bottom plate. The electrons are repelled. When the electrons are repelled, you have electrons traveling and building up charge on the bottom plate. And so you have a buildup of negative charges on the bottom plate right there. When you have a buildup of charges, there's a difference in potential. And we call that as voltage, capacitor voltage, VC. So charge builds up on the capacitor plates, the difference in the potential, we define it as VC. Now, electrons are moving, let me see if I get this right. This is moving this way, okay. So electrons are moving this way and they're moving this way, right? So they're moving counterclockwise. So continuously we see that there is movement and flow of electrons. Even though none of them are actually going through the capacitor itself, there's still flow of electrons this way, counterclockwise. So we say if the electrons are moving counterclockwise, we say that current is moving clockwise. If current is moving clockwise, you see it follows the same sign convention. Make sense? Now, in a circuit, we will say that current is actually moving through the circuit. Physically, as I just went through, I just explained, no electrons are crossing the capacitor. Okay? So don't get too bogged down into the physics of things. This is just what I use for the explanation for this one slide. After that, we'll always refer to as capacitor current. current flowing through a capacitor. But I want students to understand, when we say current flow through a capacitor, it's not actually flowing through the capacitor itself. Does everyone understand the difference? Right? So physically, there are no electrons going through the capacitor, yet we still say capacitor current or flowing through the capacitor itself. All right. Any questions? Okay. So now VC at some point is going to reach a maximum value, which would be Vs, right? So at that point where Vc equals Vs, we say it has reached full charge. So here, Vc has a value of Vs, and we say that it has reached full charge. What happens then? There is no more charge imbalance. Vc is equal to Vs. Since there is no more charge imbalance, electrons will stop flowing. If electrons stop flowing, current stops flowing. If current stops flowing, I goes to zero. I goes to zero means capacitor acts like a open circuit. So when Vc equals Vs, I equals zero, capacitor is referred to as, actually let's write it, capacitor is open circuit. So that's the physical explanation for how a capacitor would, act like an open circuit when it's fully charged. Yes. Yeah. And so a couple of slides later, I will look at the mathematical equation, and that's when I pointed out. Yeah. But does all of this make sense? Right? It's a micro level physical explanation for the capacitors. Now, you could technically remove that capacitor out. You remove the capacitor out of the circuit, and it should hold that charge, that stored energy indefinitely, right? Vc, it's storing Vc, so it should hold Vc indefinitely. So you can plug the capacitor into the voltage source, let it reach full charge, you take it out, capacitor should hold that charge, right? But it doesn't. In real life, it doesn't. Why? Because the insulator is not ideal, right? All the materials that we use in real life are not ideal. So a insulator that is not ideal is going to allow some electrons to flow through itself. Be a very, very slow trickle, but it will allow it to go through. It will allow the electrons to go through the plates. So a real life capacitor is modeled with a capacitance, and it's modeled with a resistor in parallel. The resistor is of very high value. Well, high value is very high resistance. Very high resistance. Ideally, that resistance would be infinite, right? Ideally, that R would be infinite. If that R is infinite and the capacitor is charged, nothing is going through that resistor. Everything remains across the plates of the capacitor. But in real life, it is not infinite. It has a very, very high value. So whatever charge you have across the capacitor will slowly trickle through that resistor. The resistor, of course, dissipates energy in the form of heat. So all of the charge that is stored in the capacitor is slowly dissipated. Okay. Now, real life capacitors are very, very small, like really tiny in terms of like storage capacity. So as soon as you unplug a capacitor out of a circuit, like within a few seconds or even a few milliseconds, the charge will be gone. Some capacitors are really big, like 10,000 microfarads or 1,000 microfarads, something like that. So in millifarads, when you have capacitors, large capacitors, and you take it out of a circuit, this example here shows you a charged capacitor. And here, you take that charged capacitor and you short out the two terminals. What happens? It's going to discharge, but the resistance of the wire or the two terminals, what is the resistance? 0. So if R is 0, then I is infinite. So you get a spark. All of the energy is released in an instant. So if you take a capacitor about like medium size, maybe 1,000 microfarads or 2,000 microfarads, and you charge it up and you take it out of a circuit and you short the two leads, you'll see a small spark. And that's that's also the reason why they tell you not to short out terminals of a battery, right? With a capacitor. So let's go on a tangent and use a real life example. Everyone, not everyone, but does anyone remember the Galaxy Note 7? That smartphone, exploding smartphone that came out a few years ago. So that smartphone, what they were trying to do was the battery engineers, they were trying to make the batteries thinner and thinner and thinner. And so the separation between the cells of the battery was very, very thin. And that resulted in the battery cells being shorted out. So when they were shorted out, all of the energy of that cell or that battery is released all at once. Now with a capacitor, when that happens, in the capacitor, you short out the terminals, capacitor's storage is finite. You have a spark, charge is released, and it's done, it's empty. With a battery, it's an electrochemical cell, so there's still a lot of chemicals in there. So it will keep releasing the energy until it's empty. Well, by the time it's empty, it overheats, and boom. And that's what actually happened in real life. And that's what they also tell you, right? Not to put batteries like in backpacks or in pockets along the keys and coins, is so that it accidentally shorts out the two terminals. Then all of the energy of that battery is released all at once. And then again, explosion. So with a capacitor, when you do that, again, finite amount of charge, releases all at a spark. With a battery, you get an explosion. So it's always safer to use a resistor. So you plug a resistor across the terminals of the capacitor. The capacitor energy is discharged to the resistor. Resistor dissipates in the form of heat. It doesn't matter how small the resistor is, as long as it's present, it will help in keeping the current limit, right? Okay, questions? Any questions at all? Anyone? Okay. So the equation, okay, for the example, the equation for a capacitance is what? It's C is Q over V. What does it mean? Well, it means what is the capacity of that component to store charge, right? What is the capacity of that component to store charge? But then for every applied unit of voltage. So C is Q over V. How much charge Q can it store for every applied unit of voltage, for every 1 volt voltage? So from there, you get the equation Q is equal to CV. The stored charge is the product of the capacitance times the applied voltage. Okay, Q is equal to CV. So these are 3 small examples. I just want students to I'll just go over the examples, but make sure the students understand how the voltage and the capacitance relate to each other. So in the first one, you see we have a applied voltage of 2 volts, a stored charge of 6 coulombs. That gives me a capacitance of 3 farads, right? 3 farads. In the second example, same applied voltage 2 volts, but now my stored charge is 12 coulombs. Then I need a capacitance that is twice as much, 6 farads. And if I still further want to increase my storage capacity, not storage capacity. If I want to decrease the amount of capacitance that is required, I can increase the amount of voltage. So if I increase the voltage to 8 volts and I still keep the charge the same as 12 coulombs, then my capacitance is only 1.5 farads, right? So using this equation, designers can come up with different sizes, different capacitances that can fit their circuitry. Electronics, you might be limited in the amount of voltage or current that is being supplied, right? If you have a smartphone, then the batteries are typically about 3.6 volts. Laptops work with like 18 or 19 volts. Most electronic devices work with 3.3 or 5 volts. So the amount of voltage is limited and it's fixed. And so everything else can then be changed based on that voltage. Make sense? Right? So from this equation, we can derive the VI equation for a capacitor. Right? Q is equal to CV. Q is charge. Current is the rate of flow of charge, which is dQ over dt. You plug that in and you obtain, and you rearrange the terms, and you obtain I is equal to C dV over dt. So capacitor current I is C dV over dt. Now, if capacitor is the only component, then you don't need to use a subscript notation, but other times we would use a subscript notation of C. So we would call it C times dVc over dt. And of course, it's a function of time. And so it's C dVc over dt. Same thing as the inductor equation. The inductor equation said V, inductor voltage VL is L di over dt. Everyone remember that? Right? Inductor current inductor voltage V was L di over dt, where it took the derivative. So the exact same equation, but the V and I are flipped. They're switched. And C is NL. But that's obviously given. So now if I wanted to find, well, actually the voltage, we'll take a look at it later. One more thing about that, mathematical explanation for the explanation that I gave before, right? Mathematical evidence. I of t is C dV over dt, rate of change of voltage. If voltage is constant, it's not changing, then the rate of change of voltage is 0. So I is 0, right? If the voltage, the applied voltage is constant, reaches a steady state, meaning it is not changing with respect to time. You apply a DC voltage to a capacitor, the voltage across the capacitor does not change, then the DC or the steady state behavior, current I goes to 0, the capacitor acts like an open circuit. Mathematical proof or mathematical evidence for the explanation, the physical explanation that we just did earlier. Make sense? Right? Same thing with inductor current. Inductor current was, if the inductor current is constant, di over dt would be 0, then the inductor voltage would be equal to 0. Right? Current passes straight through, no opposition. Here, capacitor acts like an open circuit. Now, if you wanted to find the capacitor voltage, if we were given the current, we integrate both sides. So I'll explain each and every step of this equation. I is C dV over dt. You integrate both sides. You take C on the other side. You get V equals integral of I. Right? Integral of I. Okay. First, let's talk about the limits of the integration. Minus infinity to t. What does it represent? Well, you're beginning your analysis at t0. And then you're going to stop at time t. Right? So t0 is the beginning of your analysis. T is when you will end. Minus infinity is all the way to the beginning of time. All it represents is basically the initial stored energy in that capacitor. It's some time in the past. So minus infinity to t0 represents initial stored energy in the capacitor. That's all those limits mean. So when you're trying to find the voltage across the capacitor, we have to take into account all the initial stored energy. So let's say initially the capacitor had 2 volts. Then you apply a further voltage to it. Now it's going from 2 volts to whatever you applied, right? So you have to account for those initial 2 volts also. And that's what is represented by minus infinity to T0. Okay, does that make sense to everyone? Right, it represents the initial stored energy in that capacitor. So Vc of T0 is the initial stored energy, or it represents the initial stored energy, initial voltage in that capacitor. And then Vc T0, if not given, you can assume to be 0 volts. Assume to be 0 volts. The limits of the integration clear? Okay, then let's talk about the variable. Now, if you recall, when I talked about the inductor, I mentioned that the variable and the limits are both the same, and it can get confusing. So in many E textbooks, we simply change out the variable in the first step itself, and that's what we are doing here. This is just the variable, and we change it to X. That's all it means. Doesn't mean anything else. We're just changing out the variable of the integration to X. You could change it to Y, Z, A, B. Does not really matter what you change it to, but you're just changing it out. That's all you're doing. So that's where that X comes from. So you have V of t dot dt instead of V of t dot dt. Sorry, I of t dot dt instead of I of t dot dt. You're doing Ix or I of x dot dx. In the end, the limits of the integration are t, so our final answers would be a function of time anyway. Okay, but when I solve problems, I tend not to do that, but I leave this slide on here on purpose just to explain to students. So if you ever read a book or if you're taking someone else's class and you see a change like this, well, that's the purpose of the change. That's all. We just change out the variable. Does that make sense? Right? So now Vc of t is 1 over c integral 0 to t I of t. Power is still the product of voltage and current. So Pc of t is Vc of t times Ic of t. You plug in I is equal to c dv over dt, and you obtain equation for power as Cv dv over dt. Cv dv over dt. You integrate the power, and you obtain equation for energy as half Cv square. Half Cv square. Please make sure you upload your campus pass. There are quite a few students who are still missing. Okay, inductor energy, stored energy was half Li square. Capacitor is half Cv square. Inductor, we deal with current. Capacitor, we mostly deal with voltage. What happened? Okay, seems to be working. What happened? Okay. All right. So let's get into examples. I have, let's see, how much time do I have? About 19 minutes. So we have time for 3 examples. Okay. One important point about the examples are that all 4 examples use capacitor as the component. Okay. But the examples and the methods will apply equally to an inductor also. So let's solve the first one, then I would show what a inductor example might look like, or inductor question might look like. C is 5 microfarads. We are asked to find the current. And I of t would simply be C V over dt. C is 5 microfarads, and derivative of t. Okay, let's see what we have. Cos x, derivative of cos x is minus sine x. So we take the minus sign out front. Then we have, what do we have? 6,000. And then we have 10. And finally, sine of 6,000 t. Right? We reduce all the numbers and we get minus 0.3 sine of 6,000 t amps. Right? So again, cosine and sine functions are something we'll look at in chapter 5, but for now, you don't really need to know what it is or what it does. We're simply taking the equation, plugging in the numbers, and just solving it. Right? So you have derivative of cosine is sine minus sine, right? So you take minus outside, 5 into 10 raised to minus 6, 6,000, 10, reduces to 0.3, you get minus 0.3 sine of 6,000 t. Easy enough? You're just easing in. The same example, the same problem could be asked for an inductor. Let's say inductor is given to you as 5 millihenry, and I of t was given to you as 10 cos 6,000 t. Find V of t. And of course, V of t for a inductor is L times di over dt. Right? So the same problem can be asked of an inductor. Inductor value is so and so, and then I of t, inductor current, is given to you as something. Find V of t. Simply plug it into the equation. Solve it the exact same way. Does everybody understand? Right? So the examples are all about capacitors, but they could apply equally to a inductor also. So the four problems that I'm going to solve, the first one, voltage is given, find the current. So you perform derivation on this. Second one, the current is given, find the voltage. So you now integrate the current. And problems 3 and 4, there again, first one, voltage is given, find the current. Second one, current is given, find the voltage. But those problems 3 and 4 apply to a technique called piecewise linear analysis. Okay. Again, they all use capacitors, but you can use the same techniques to solve for an inductor also. So let's look at problem 2. In problem 2, we are given a capacitor of 2 microfarads. I of t is given to us. V of t obviously is 1 over c integral 0 to t. And this time I'm not going to change the variable. I'll keep the variable as t. Okay. I don't want to, unnecessary complications. So it's 6 times e raised to minus 3,000 t dot dt. Very good point. Yes, absolutely. So I was going to ask, but you preempted me. I was going to ask, what am I missing on there? So it's got to be 3000 t times 10 raised to minus 3 dot dt. And then v of t0. Now, there is no specific mention of initially stored charge. So we assume this to be 0. Effectively, we won't consider it, right? It's completely discharged capacitor. Okay, so let's plug in the values. 1 over C is 2 microfarads into 10 raised to minus 6. We'll take 6 and 10 raised to minus 3 outside. 6 into 10 raised to minus 3. Then we have e raised to minus ax. So we get e raised to minus ax divided by minus a. T inside the brackets is the variable. Outside is the limit of the integration. So 0 to t. And then reduce it, and you get minus 1 e raised to minus 3000 t minus e raised to 0. And therefore, v of t finally reduces to 1 minus e raised to minus 3000 t. And this would be volts. Let's take a 10-second pause. Let me know if you have any questions. Make sense? Right? So again, after you plug in the equation, then it's math from that point on. Now, if this was an E class, we would give you the value of t, and we would ask you, find the voltage when t is equal to 5 milliseconds, and plot the entire graph for, let's say, 0 to 10 seconds. Again, you have an equation, you have a function, you plot in different values of t. You can plot this in Excel, MATLAB, any software of your choosing. You can plot it by hand if you wish. But this is, for 201, we don't do that. E major class, we do the same thing, but we derive the equations. We go again, we don't snorkel, we go a little bit deeper into the material. So we can plot this function in any software or any manner. Okay. Any questions? Yes. I don't know. I haven't decided yet. It's a good question. We do that for the E major classes. We don't do it for non-major classes. So there's your answer. You won't have to do that. No. Yes. I can understand. It's not my favorite topic either. So. I think it'll be both. I'll have a common final, and for those who don't want to take the common final, they can take it at the regular schedule time. So I'll send out more information. So it's not automatic. We have to send a request to the administration, and if they can find the space and they approve it and everything, and that doesn't happen until later. So it's not in my hands. I mean, I will request for a common final, but whether it's approved or not is up to them. But I will have both options. So some students like to take it Saturday, get it out of the way of finals week, and then concentrate on the major classes during finals week. So some students like to do that. So yes. Yep. So students, If the common final is approved, then you can take the common final on Saturday, or you can take the final at the regular time that's posted on Canvas. Either ways, your choice. But again, we'll talk about that if and when it's approved. The final exam date on there, by the way, is current on the Canvas webpage, right? Okay, here, this waveform describes, it's a graphical representation of a voltage that is being applied to a capacitor of 5 microfarads. We are asked to find the current. There's no mathematical representation. There is no equation that could describe this waveform. So what we do is we break it up into pieces, and we get a technique that is known as piecewise linear analysis. Why? Because every piece will be linear. So in this case, again, this is a simple waveform. You can break it up into 2 pieces. And I would say time period 1 goes from 0 to 6. Time period 2 goes from 6 to 8. And this is milliseconds, by the way. Milliseconds. And each piece is linear with respect to time. Right? Now here's the beauty. If it's linear with respect to time, you can write a mathematical expression for that piece in terms of the slope. And what is it describing? It's describing voltage as a function of time. So the slope of this graphical description, graphical line, is basically the rate of change of the voltage, dV over dt. So you break it up into pieces, you find the slope of the line, you multiply it with the capacitance, and it gives you the current. Nothing more difficult than that. Basic high school math, actually. Yes. Yep. Yep. And there are, I think there is a, I have notes on Canvas. I think there should be a document on Canvas which has, let's see, I think I posted all of the documents before. So yes, it's there. It says piecewise linear analysis. These are my handwritten notes and solve 2 problems. But it's a self-contained piece, meaning I explain everything. Every step in there is explained. So this is the exact example. So the question being asked was, what if the voltage is a constant, but it's above 0? So as you can see here, right here, the voltage is a constant between 2 microseconds and 4 microseconds. It has a constant value of 10, right? So when I solve this, IC of t would be 0, right? So for that portion between 2 and 4 seconds, capacitor current is 0. Oh, nobody's, I'm not that scary. You can interrupt me. Come on, come on. Okay. Okay, so on the website, if you go to lecture slides, right here, piecewise linear analysis, it contains 2 solved problems. They're different problems, so definitely go over the problems. And let's see, oh, not that. So here you can see the voltage between 2 and 4 microseconds is 10. It's a constant. So when you find the current, it's going to be 0. And so when I plot it between 2 and 4 seconds, current for that capacitor is 0. Make sense? Right? All right, let's go back to our current problem right here and finish solving this. So for T1, we need to find the slope. So what we're going to do is we're going to find M1. We find the two coordinates. X1, Y1 is 0, 0. X2, Y2 is 6 milliseconds and 24 volts. So M1, which should be Y2 minus Y1, over X2 minus X1, gives me 24 over 6, gives me 4,000 volts per second. Therefore, my current I of t is C times M1. C is, what is C? 5 microfarads. Therefore, I of t would be equal to 20 milliamps. Easy enough, right? dV over dt, rate of change of voltage. So you break it up into multiple pieces. Each piece is linear with time. You can use the slope line intercept method to actually describe that voltage also, which is on the handout that I've posted on Canvas is a second problem. So both problems are solved the same way, but the second problem asks for power. Then you need to write an equation for V of t, meaning you need to write the actual equation for the line, not just the slope. We only find the slope here because we only need the slope, right? C dV over dt. But if you want to find power, P of t, then you need the equation for V of t also. So then you need to describe V of t. Does that make sense to everyone? So please go through the handout on the website. Let me know if you have any questions. I still have 2 minutes and I still have the second time portion to finish. So T2 would be M2. M2 would be, what would it be? 0 minus 24 divided by 8 minus 6 milliseconds. And so I have minus 12,000 volts per second. Therefore, I of t is equal to 5 raised to minus 6 times minus 12,000. And therefore, I of t will be minus 60 milliamps, which if you plot it out, you get 20 here and minus 60 here. Okay, any questions? Well, now we are done. Still, there's a minute left, but you're free to go. I'll see you all on Friday. We'll wrap up this chapter with example 4. Homework is due tonight, but it'll be pushed back till Saturday or Sunday. Okay? Okay, homework is due tomorrow, but it'll be pushed back to Saturday or Sunday. Yeah. Transients, I believe. So, yeah. Yeah. No. Yes.